Hey guys, we are going to talk about Descartes' rule of signs. You might be reading that as Descartes. It's Descartes. I found this funny YouTube video. I don't know why I think it's so funny. Probably because I want to make my own version of it. But see, I'm not lying. Descartes. Okay, sorry. I don't know why I thought that was so funny. Okay, so let's talk about Descartes' Descartes' rule of signs. Let's first talk about Descartes' rule of signs. So we have this polynomial function down here as an example. It says, if the terms of a single variable polynomial with real coefficients are ordered by descending variable exponent, in other words, it's in standard form, then the number of positive roots of the polynomial is either equal to the number of sign differences between consecutive non-zero coefficients or is less than it by a multiple of 2. And knowing some of you, you're probably like, huh? What? So we'll talk about what this means in a second. I just want to highlight the big thing here. The number of roots of the polynomial is equal to the number of sign differences between consecutive non-zero coefficients, or it's less than that by a multiple of 2. Another important takeaway is that the number of negative roots is found by the same process using f of negative x. Multiple roots of the same value are counted separately. Okay, so Descartes' rule of signs probably is not as useful now that we have a graphing calculator, kind of like our rational root theorem, but we still learn this to gain an appreciation for mathematics, right? It's still important to learn this. I mean, think about Descartes, out of nowhere came up with this, honestly. So it's important for us to gain that appreciation of what he did and how that works the longhand way, even though we do have our calculators. Sorry, my voice is awful. Maybe you'll remember me being sick a while back. Still am. Can't get over it. Why not? I don't know. Okay. So, sorry. As you guys are aware, these things are just like crazy and hate me. So, okay, so let's start by using this right here. And we're going to figure out how many positive roots it has. So if I'm looking from term to term, here's a term. Okay, now let's focus in on where the sign changes. So it goes positive to positive, positive to negative. So there's my first sign change. Negative to positive, another sign change. And positive to negative. So 3 sign changes. So if I want to know how many possible positive roots I have, positive. Like it says up here, it's either equal to the number of sign changes, so 3, or it could be the difference between this by multiple of 2, which 3 minus 2 would be 1. Okay, so this, we're taking a look at number of sign changes. So just note here, there must be at least 1 positive root. Okay. We know in total that there's 4, right? Because the degree is 4. So it's either 3 positive roots or 1 positive root. We know there must be at least 1 because it wasn't like 4 to 0, right? So at least 1. Now this part that I highlighted in blue here, the negative roots. So in terms of negative roots, I'm not going to spend time doing it right now, but if we use a different color, we would have to see what f of negative x looks like and then look at the number of sign changes there. And just so you know, if you want to do this on your own, because you don't believe me, that would be 1. Okay, so you could totally on your own do f of negative x and see how many times we have sign changes. Okay, so without a calculator, okay, we have given f of x, the same f of x. We want to put everything together. We want to list the possible rational zeros. So that will be using our rational root theorem. Maybe let's make a note to ourselves. That's what we're using. Rational root theorem. That does not stand for rah-rah tia, okay? Rational root theorem. Then we're going to find all the zeros using the rational root theorem and the x-intercepts, which are pretty much the same thing. So x-intercepts are ordered pairs in the graph, and they're real. And then we're going to write the polynomial as a product of linear factors, okay? So let's start by using the rational root theorem. Figure out our p's. Remember, p's are factors of our last term, our constant. Give me plus or minus 1, plus or minus 2, plus or minus 4. Q would be factors of our leading coefficient, which in this case is 3, which is plus or minus 1, plus or minus 3. Therefore, P over Q would be all of the possible combinations of these. So it's going to be 1 over 1, 2 over 1, 4 over 1. Don't forget plus or minus. And 1 over 3, 2 over 3, 4 over 3. Nice. So again, just so we understand what this rational root theorem is saying, it's saying that these are the possibilities of rational roots of this polynomial. Remember, rational means it can be written as a fraction. So one of these guys in here has to be that. So, you know, back in the day, because I'm so much older than all of you, you have to go and, oh my goodness, what the heck? Stay. Okay. Back in the day, you'd have to use synthetic division for all of these until you found one that had a remainder of 0. But I'm just so smart that I happen to know that if I do -2, it'll probably work out. How would I know that? What's a shortcut way of this? You could graph your polynomial f of x. Find one of your x-intercepts, which should come from this list, which you should see an x-intercept at -2. And then choose to synthetically divide by that. All right. Does anyone else get a kick out of synthetic division? Just me? Okay. So synthetic division. Here are all my coefficients. Let's drop the first one. 3 times -2 gives me -6. 4 plus -6 gives me -2. We're probably all pros at this now, right? Better be. -6, -2, 4. Boom. Yes. All right. Remainder of 0. That's what I wanted. Okay. So remember, let's build up remainder, constant, x squared, x cubed. It makes sense that this is x cubed because think about, I just divided an x plus 2 polynomial by an x to the 4th power polynomial. So that makes sense that this is 3x cubed. So let me just rewrite this now. Okay. So I'm looking at this and I'm like, hey, this factors, this rules. So we're going to do factoring by grouping. Now, let's say that this didn't factor by grouping. We would have to use our new polynomial, go through the same awesome process, right? Rational root theorem, find a 0, synthetically divide, and keep going. But don't have to do that this time. So, factor by grouping. Boom, boom. Take out our x squared term. GCF plus, technically there's a 1 in front here. I like to write it just because sometimes students forget that this is x squared plus 1. I know, silly of them, right? So now I have x squared plus 1, 3x minus 2. Okay, so at this point, let's just start listing our zeros. Okay, well, for sure, from original here, from synthetic division, we know one of our zeros is x equals -2. From this bad boy here, we have x equals 2/3. And from x squared plus 1, we would get plus or minus I. Which if you're not sure where I get that from, here's a little side work for you. Which the square root of -1 is I. Okay, so that's where that comes from. It did also ask for x-intercepts, so let's list those. So x-intercepts we like to write as ordered pairs. So -2, 0, and 2/3, 0. Cool. Okay. Also, notice that we have one negative root and one positive root. And that kind of takes us back to Descartes' rule of signs, which we talked about that would happen in this case. The last thing that we were asked to do, if you look back at the directions, was to write the polynomial as a product of linear factors. So f of x equals linear factor of this 0 would be x plus 2. Linear factor of 2/3 would be x minus 2/3. Or you could have written it as 3x minus 2. Doesn't matter, they're both linear factors. And then we had two more zeros here for roots x minus I, x plus I. Dang, that was a lot of work, but feels good, makes sense, at least to me it does. All right, so just a quick conclusion here. Descartes' rule of signs tells us how many possible positive roots and possible negative roots a polynomial will have. Thank you guys for taking good notes.